Good afternoon. So my name is Jeroen Vandenbruwane. I'm the Managing Director of Injectis. We are a small Belgian company specialized in injection of reagents in the soil. And the story that I will tell this afternoon is working further on what we've seen this morning. We've seen a lot of very interesting presentations on lab scale and very small field scale applications on the degradation of lindane and HCH. This is the outline of my presentation. So I will start with the different in situ soil remediation techniques or processes for lindane and HCH. Then I'll show you some conventional injection techniques and also the technology that we use to inject the reagents into the soil. Just briefly, when can we go to an in situ treatment of lindane? If we look to the high concentrations in the unsaturated zone, well, their excavation is the most suitable and the most sustainable way of treating the pollution. If we look to the very high DNAPL concentrations, well, there a physical removal of the pollution is needed because in situ treatment needs an aqueous phase, and with DNAPL you don't have the aqueous phase to get the process going. So in situ treatment of lindane and HCH is only possible for residual DNAPL concentrations and dissolved plumes. As mentioned this morning, I won't repeat it, aerobic biological degradation is a possibility for lindane and HCH. Anaerobic biodegradation is a possibility with the degradation, the first step, an anaerobic step to chlorbenzene and benzenes, and then an aerobic step to CO2. In situ chemical oxidations, there are two possibilities for lindane and HCH. It's persulfate, activated persulfate oxidation, and Fenton's reagents. I just mentioned for your information, so if you want to oxidize with persulfate 1 kilogram of HCH, you need 10 kilograms of sodium persulfate. Just to mention that for DNAPL concentrations, to my opinion, chemical oxidation is not suitable. The same with Fenton's. For 1 kilogram of HCH, you need 2.5 kilograms of hydrogen peroxide. In situ chemical reduction is also a possibility. Therefore, we use zero-valent iron, in which the lindane is reduced to benzene and chlorine, and the zero-valent iron is oxidized to ferrous iron. 1 kilogram of HCH needs only 0.6 kilograms of zero-valent iron. And the last process or last technology for in situ treatment of lindane could be also sorption. So if you have very low concentrations of lindane, you can try to sorb it to, for instance, biochar, activated carbon, or stable natural organic matter as compost or stable microbial biomass, or some minerals like bentonites, zeolites, and so on. All these processes, all these in situ soil remediation processes for lindane and HCH, they are all based on the principle of adding something to the soil, adding something to the aquifer, which gives a certain reaction. So therefore, a certain substance or a certain chemical or a certain product has to be brought into the soil. To our opinion, there are three factors influencing the quality and the final concentrations of an in situ soil remediation. First of all, you have to know where your pollution is. You have to know what concentrations are present and also the biogeochemical conditions of the aquifer. A second condition is that you know what reagent to use. So you have to know what reaction you want to stimulate in situ. If you know what reaction, you have to choose what reagent fits best in the certain environmental conditions. And then you have to calculate how much reagent do I have to add to the aquifer to get the right reaction. And a third factor that is frequently overlooked is that you have to get the two in contact. You have your pollution, but you have to bring your reagent into physical contact with your pollution. So you have to choose the right injection technique. You have to know how much liters do I have to inject in a certain depth to get a certain radius of influence. You have to know how far do I have to put my injection points or filters one from the other. And you also have to know what is the injection pressure. And only if all three conditions are optimized, only then you will have a successful in situ soil remediation for lindane or HCH. Pressure, that's the following slide. We know that the pollution is present in the natural porosity of the soil. So what we want to do is also inject the reagent in the natural porosity of the soil. And we figured out that injection pressure is the key parameter. So if on the x-axis, this is the pressure, this is the depth beneath the soil surface, and at a certain depth, the injection pressure has to be high enough to overcome the hydrostatic pressure of your groundwater. It has to be high enough to overcome the capillary pressure of your water and your porosity, but it can't exceed a certain fracturing pressure. And fracturing pressure, that's the pressure of your natural soil at which you create an artificial fracture. So at every depth, you only have a very narrow injection window in which you can really inject in the natural porosity of your soil. And that, the width of that injection window depends on your soil depth, which is obvious, depends on the groundwater level, and it also depends on the pore dimension, so on your capillary pressure of your soil at that given depth. To go to the conventional injection techniques with that thing in mind, what injection techniques do exist on this moment? Well, you have soil mixing, which is in fact technically not an injection technique because it's a physical mixing of reagents with the soil. You have recirculation on fixed wells, so you pump the groundwater, you add reagents and you re-inject in fixed wells. You have the same principle as recirculation, but you don't pump your groundwater, you only inject reagents in several points. And finally, you have direct injections. So 30% of the in-situ remediations are done with direct injections. And with direct injections, an injection rig is used and an injection head is pushed or drilled into the soil, and from that injection point you inject the reagents in the geology. If we look to injection on wells and recirculation systems, it's very good in homogeneous sandy aquifers with rather short filter screens. And there you can quite homogeneously inject your reagents. It's no problem, so you have very low capillary pressure and you can inject at low pressure. It's also a low-cost technique to inject your reagents. In silty clays, on the other hand, and also in heterogeneous soils, the capillary pressure is much higher, so you need a higher pressure to inject, which which gives the risk of fracturing the soil. Also in heterogeneous soils, with filter screens that are installed in the different layers, your reagent will preferentially enter in the layers with the highest hydraulic conductivity, so in the layers, the sandy layers, and not in the clay and the silty layers, whereas most of your pollution is just present in the clay and the silty layers. So after injection on wells in a heterogeneous profile, what is frequently seen is that you get rebound, so your pollution is liberated from the clay and the silty layers back in the sandy layer, and you can start all over again. If we look to the conventional direct push technology, in principle, they can inject the whole profile. It's also very efficient in sandy aquifers because it's easy to inject. You have low capillary pressure. You can adapt, in principle, the pressure as a function of soil depth, and it's relatively cheap to perform. On the other hand, if we look to silty and clay layers, you need a higher pressure to inject, not only because of your geology, but also because of the design of your injection head, which compacts the soil around your injection head. And you are forced to increase your injection pressure to break through that compacted zone. So frequently, the natural soil is fractured. And fracturing means that, in fact, your reagent is pushed or injected in an artificial fracture and is hence not in contact with your pollution present in the natural porosity of the soil. Same story for heterogeneous soils. So you really easily inject in the sandy layers, but again, in the silty layers, you have to fracture, and you will also get the rebound afterwards. But there are a few advantages of the direct push technology. Well, it's fast, and also you don't need to install a permanent infrastructure, which makes the technique very flexible. And on the basis of these advantages, we developed the spin injection technology. Instead of hammering an injection head into the soil, we developed this injection head, which we drill into the soil, and which allows us to inject in the open porosity of the geology. So we can use lower injection pressures. We open the soil progressively, and the hydraulic conductivity of the soil is not altered. We combined this injection head with a microprocessor and a pressure control system, which allows us to adapt the injection pressure as a function of soil depth, but also as a function of the groundwater level and the texture, or the soil texture, or the capillary pressure at a certain depth, which allows us not only to inject in sandy soils, where we have in fact no technical advantage, but certainly in silty clay or clay soils and heterogeneous geologies, we can make the difference with the conventional injection techniques. Thank you for your attention. If you have questions.
Thank you very much, Jeroen, because you made part of the introduction of my presentation, because you mentioned that the key when you made some in-situ injection is the contact between the pollutant and the reactive. That's right. And sometimes when we have a very high velocity aquifer, it's not that easy to have this sufficient contact time between the pollutant and the reactive. This is my point, because this project has been done in this type of context. Another thing is when you inject solution, everything you inject pass where it's easy to pass. It passes where it's more permeable. And you still have this less permeable layer that stock the pollutants, that fix a lot of pollutants, and then diffuse pollution. So it's quite hard to target this type of less permeable layer. And we think this polymer gel I'm going to present you is able to get into the less permeable layer to treat effectively the pollutants. So two goals: to optimize resistance time and to get where it's really hard to get into. So it was a project made with some university, but also a private company, funded by an environmental French agency. And so the goal was to improving the treatment in this high velocity aquifer. So we made different laboratory tests and we choose one technology, this alkaline gel I'm going to present to you. Here is the context. So you can see here alluvial materials, very coarse material, groundwater table 8 to 10 meter depths, and a groundwater flow really high, 10 meter a day. You can see that we have really high concentration. We are talking about soil concentration on industrial sites, several dozens, several hundreds of milligrams per kilogram of lindane and isomers. And our main objectives, because there were already a plan to treat the non-saturated zone. So the objective here was to find a solution to treat the capillary fringe and the first meters of the aquifer. So the goal was to treat lindane, but we used the alkaline hydrolysis just to transform lindane into trichlorobenzenes. Our main goal was to test the gel. So lindane and isomers are persistent organic pollutants. It have low mobility and low vapor pressure and solubility, so it's quite hard to extract from the soil, from the groundwater. On the contrary, with trichlorobenzene, it's not listed as a POP, of course, and it's also more mobile and more volatile. So the idea was to transform into trichlorobenzene and then to find a classical solution to treat trichlorobenzene. So we wanted to pass from a non-treatable option within the site condition, because of the high velocity of the aquifer, to something that could be treatable in that conditions. I'm going to present you the lab experiments we've done. So you have to imagine these 2D devices. So between two plates of glass, we have sand, time -3 meters per second, and here a small gravels, 10⁻² meters per second. So we are going to simulate the groundwater flow from the left to the right, and here the cross represents the injection point, okay? So first test is injecting an alkaline solution, just aqueous solution. So we inject in the more permeable layer, then we activate the groundwater flow simulation, colored in orange, and you can see, of course, that was expected, that everything is flushed. Then we've tested this reactive alkaline gel. So same story, we injected here in this layer, then we activate the groundwater flow, and you can see that whatever the groundwater is flowing during time, we still have this gel remaining stable in the medium. And you can also see that the gel is also propagating a little bit in the less permeable layer. So it was really interesting. 5 days, 10 days, 18 days, we still have this gel, and we still have this alkalinity, because you can see here the color of what has been injected. So we still have alkaline effect to transform lindane. So the dissolution is very low. The lifetime at lab scale is only 3 weeks, and the alkaline reagents remain stored in the gel. So let's go to the site. Here can see here the context of this industrial sites, the different injection points in blue, also in green, and here the monitoring wells, the groundwater flow direction from south to north on this map. So we prepared this gel thanks to a biodegradable gelling agent, it's xanthan, alkaline reagent, it's soda and water. We mixed it in a containerized unit we built at this, for this occasion. So just a brief look to this containerized unit system. And we obtain, here you can see this alkaline gel, pH is around 13, and the conductivity is quite high, and as you'll see just later, it's a key important to observe by tomography the propagation of the gel. And here, the injection well, what has been interesting in that during the injection of gel, there was no increasing pressure during injection. So we had really good radius of injection without any increasing pressure. So 25 cubic meter of gel has been injected into every wells. So globally 150 cubic meter of gel. Here is the experimental plan. So monitoring, we have monitored the groundwater table thanks to automatic probes, conductivity at different depths, temperature. Manually, we also monitored, we also made some digraphy and hydrogeological assays to estimate the groundwater flow velocity, and analytical monitoring, you know, classical ones. And of course, pollutants, lindane and isomers, and also byproducts. And we also monitored at the end of the project the potential creation of dioxin and furane, and it was not measured at all. One of the objectives was also how can we observe the propagation of the gel into the system. So we use electrical resistivity monitoring. We have implemented electrodes in existing wells, and we made picture between the different electrodes to finally obtain here the 2D images. And then we have created this simulation. So this is the initial condition. So you can see here that the conditions are not conductive because there is no gel yet. And when the color is becoming blue, that means that there is gel really conductive with presence of soda. So initial condition, 1 cubic meter, 2, and you can see here the evolution of the resistivity. So the media, the system is becoming more and more conductive. We continue the injection and the color is becoming more blue, so more conductive. Then we stopped the injection. We went back on the site 4 days later, and we still observed that we have gel on the site. So this was the first step of this treatment, of this pilot. So then we injected the totally, what was planned to, the global quantity of gel that was planned to be injected. And there were no visible differences after 25 cubic meter injected. And we know, because we observed also the gel beyond the surface where we were monitoring with tomography resistivity. So the gel arrived 10 meters even upstream. So we observed the gel upstream, downstream, and with this type of radius of injection that was not expecting to be that high, to be that larger, without any pressure. Now you know. And we went back on the site 10 months later, and there were still a huge quantity of gel in the system. So even if we have this high permeability, this high groundwater flow, the gel is remaining on the in situ. And concerning the results, so here this was the injection point where we inject the gel, and here we made some drilling, soil drilling. We analyzes HCH and subproducts to make the final characterization. During the sampling, gel was still present also on the cores. And here are the results between 8 and 12 meter. Initial concentration, this is in milligram per kilogram, so you can see the high concentration of lindane in the aquifer and what is the final situation. So the median of the concentration was 146 milligram per kilogram, and at the end we had this really low concentration, so this great degradation yield. And even if we observe the result between 0 and 15 meter depths, we have these great results. So concerning the groundwater, we observed even upstream that after the injection, we have kind of maybe just flushing a little bit concentration of lindane, but then no more lindane concentration, and downstream from initial characterization to final characterization, we had this great abatement. So at the conclusion, gel was very interesting to disperse this reagent into the soils, even if the velocity of the groundwater was so high. So we are not expecting such results. The alkaline gel is very effective to transform lindane into trichlorobenzene. That was not maybe a surprise, but to have so homogeneous results on the volume that has been treated, it was very positive for us. And yeah, the gel is able to strongly reduce local groundwater, because I didn't present to you, but we made some also measurement of the flow velocity, and the zone where the gel is really impermeable, so there is no flow, water flowing into this gel. And also tomography was also a great tool to monitor the treatment. And just before finishing, we had another project that is ongoing, and we plan to make some pilot tests. It deals with gel with surfactants to mobilize DNAPOL, and we already have amazing results at lab scale, and I hope I will have the opportunity to present you these results next time. So thank you for your attention.
So after long talking about lindane, I'll move into another category of persistent contaminants, because I'll touch with my presentation on PFAS, and specifically on a full-scale project we just finished on installation a barrier for managing a PFAS plume. The technology we have used is named PlumeStop. This is a liquid activated carbon. So basically it's very fine particles of activated carbon that are dispersed into a liquid, into water, and this becomes basically a black ink which can be dispersed at very low pressure inside the aquifers. So basically it turns the aquifer itself, where we inject it, into an activated carbon filter. So we are bringing sorption by activated carbon from being substantially an ex situ technology, we're bringing into in situ. And the way it's able to move, it's easily visible in this video. So basically, it's able to move homogeneously throughout the subsurface. And this homogeneity is very important because we need to bring the product and to spread it homogeneously in order to obtain good results. And this is what happens at the microscope scale. This is sands, particle of sand before injection of plume stop. And this is what happens after it. So basically, all the soil is coated by the colloidal activated carbon. What are we doing with PFAS plume? We are building up injectable permeable reactive barriers. This means a line of injection point, and we need to make sure that in the subsurface, the radius of influence would overlap to ensure the barrier continuity. So we would install this barrier just at the edge of property boundaries, or before a sensitive receptor, or before or after down gradient of a secondary source. We might wonder if these can be considered proper remediation, because what we are dealing with PFAS that are persistent contaminants, so do not degrade, we are opting for a sequestration process, so to bind them on the long term into an activated carbon medium into the subsurface. And indeed, it is real remediation, because if we recall what remediation means, it's minimization on the removal of environmental or health risk, and risk is given by exposure times hazard. So we are not manipulating the hazard, so the concentration of the compound, but we are manipulating the exposure. So binding in situ the PFAS onto the plume stop, then we eliminate any exposure pathway for potential sensitive receptors, and this eliminates the environmental risk. And then, would this just be temporary? So if I'm just doing an in-situ barrier for sorption, would I need to expect that sooner or later this barrier fill up, get saturation, and I suffer from breakthrough? Well, yes. Because we are talking about a sequestration approach. The point is when this would happen. So we are able to predict, avoid, and prevent the breakthrough. So through in-house models, we are able to predict what happens and at what stage, and based on this, we can react and do proactive activities to avoid the breakthrough moment. And on the modeling and on the concept, there is a lot of third-party articles that have been published during time. Another option we have, and this is recent, this is an innovation we just introduced a few months ago. We can act proactively on the source with another colloidal activated carbon. This time is named source stop. We can deal directly and immobilize unsaturated or saturated source. What this provides is that I prevent discharge of additional contamination that can feed the plume. So on the longer term, I reduce the amount, the flux mass of PFAS that it's able to arrive to my plume stop barrier, until the point that I can avoid any requirement for future reapplication. If this is not the case, or if this is not immediately possible, anyway, just with a plume stop barrier, we are able to provide decades of containment, of sequestration, and this is without any additional proactive activity. So it's just installation today, and then for many decades, just monitoring the effects, so completely passively. And this has been already also considered as a remediation method by the ITRC in the US, which are defining that management of PFAS plume can be done into using injection of amendments of colloidal reagents. Let's get into a case study. This was one of our earliest European case studies. It's an airport in England, and not surprisingly, the source was a firefighting training area. Contaminants of concern, PFOS and PFOA, so the most common one. And the geology is quite tricky. So it's a weathered chalk, which means that it's high and low permeability layers intercalated between them. We did a pilot test. This was end of 2020. A pilot test usually, on these cases, it's a portion of the longer full-scale barrier. So it's a number of injection points on a line, and then we get up-gradient monitoring point inside the barrier, and then down-gradient. What we observed is that up-gradient continuous influx of contamination inside the barrier immediately from the first monitoring ground arriving to non-detect. So this is this monitoring well. More down-gradient, 2.5 meters distant, also non-detect. What we are getting at 5 meters distance, it's the starting of a decline. So this is shallow layer and deeper layer. The deeper layer appears to be much more fast, this decline, compared to the shallower layer. And this is because basically what we are getting is that the deeper layer, it's faster flowing. So a monitoring well at distance would monitor first what's happening thanks to our plume stop barrier. So the results were robust enough, non-detect, 99.something% reduction, to allow to move then to the full scale. And the full scale has been already implemented. This was in 2022. Is this long barrier here? The groundwater direction is towards north, and it's a 277 meters long barrier. The installation meant 4 months of activities. It's not just the injection, it's also validating where we are placing the product. This is key. So during the installation, we ensure that we provide continuity to this in-situ barrier. After this, we do not move out from the site. So we go through another phase, we call it commissioning. It's another many months of activities where we do test, we do validate if the effectiveness of the barrier is okay or not. And we rely also on the early results that we do obtain. And this commissioning phase is just finished now, so in early February. So we have up-gradient monitoring wells, we have wells within, so inside the barrier, and we have validation wells, which are instead down-gradient of the barrier. This is the installation area. And then how do we validate the installation? So how do we confirm how we have placed the activated carbon? We can base ourselves on soil coring, on groundwater monitoring, but also we have secondary line of evidence. For example, electrical conductivity. It's a very good indicator of our activated carbon into the ground, so we can rely on this to understand where we have placed the carbon. These are very early results, so it's May 2022, so it's still during the installation phase, but already in the well within the barrier, we already got everything at non-detect. We got some issues with the detection limit. This is because still it's during the injection, so the groundwater is black because the carbon is still in suspension. So the analysis cannot be very precise. So we solve this with centrifugation to give a lower detection limit. This is something which is needed just temporary, so not then on the following months when the activated carbon completely settle down into the soil. And now we got at February, just a few weeks ago, the first results. So early February, we have released the barrier back to the client. We have finished the commissioning phase. We got the first validation of a monitoring ground, and all the down gradient monitoring wells are all at non-detect. So the barrier, it's completely performing. This complete performance is not just a matter of those wonderful results. It's also about we guaranteed those results to the client, which means that through the Plume Shield guarantee program, we guarantee to the client that the barrier would continue to be effective over time. It means that any type of reapplication, then through this case, in this case, it is for a number of 10 years. If anything happens to the results in 10 years' time, Regenesis would go back to site at its own cost. So concluding, I've showed you a strategy for dealing in sequestration with PFAS. We started first with plumes, with plume stop. We now can implement it with direct source treatment, unsaturated and saturated source, also with a colloidal formulation. And these solutions are much more sustainable compared to what is more widely used, which are all techniques that are based on pump and treat. So it's much more sustainable, not just in cost, but also on general sustainability, because it's not providing any waste and interference with activities ongoing on the site. On the sustainability, we are working also in these months for a quantitative measure of the sustainability of the solution compared to other solution. With that, I've concluded, and thank you for your attention.
Good afternoon. My presentation is going to verse on the chemical tests that we carried out at the Bailin landfill.
Okay, for any ISCO application, the test that we developed on site, and we will be focusing around the results of two tests. The first pilot in 2016 and the full scale in 2019. You know that ISCO is a remediation technology based on the chemical oxidants with the contaminants to create a reaction. ISCO is a contact sport. We have heard this before, but if there is no contact of a sufficient mass of oxidant and contaminants, the destruction or the oxidation won't happen. Application in underwater is theoretically easy. We inject the oxidants in the plume, and if everything goes fine, downstream we would reduce the concentrations of the contaminant charge. It is more difficult than said, particularly in Bailin. Here you can see the site of Bailin. Well, you know it very well so far. We carried out 4 ISCO essays. The first one in 2016 was the subject of a live project, then a full scale in the plume when there was no DNAPL in 2019, then a third one in the limolite, in the siltstones, and then a fourth one in the landfill area, direct area. Everything started in 2010 with treatability studies with persulfate as the best oxidant and the alkaline solution. In 2016, we carried out the first pilot test in a flux cell of 200 meters. In 2019, we carried out the full scale with 700 meters of the aquifer. We tried a commercial persulfate, the PERSULFOX, which was easier to inject, to apply. We carried out some tests and we wanted to just try it. In 2021, we did exactly the same in the cell stones, and in 2022, we tried a different brand. Theoretically, it's more microbial friendly, will not attack that much. It was going to reduce the biodegradation capacities, but its kinetics was not going to be that fast. We will be talking now about the test in 2016 and 2019. In 2016, in a fractured aquifer, like the one in Bailén, what we know is that any action, whether it's pumping or injection, has a very fast response. So we collect data here or here. What we can see or interpret is that nothing happened, because we knew that is that we had to sample or take many samples in a very short time, which is essentially in a fractured medium. Field work is pretty intense. We hired six person staff for different functions with level samples, water sampling, titration, etc. For conductivity profile, drafting, working day and night, titration of persulfate in order to know when the next injection had to be done. And what was the goal of all this? With all these pieces in the puzzle, it is difficult to really see the whole idea, but we needed to know the whole picture. This shows the assay, the test cell. This would be the baseline. In red lines, the fractures. In red, that means it has COX, and in green shows the first injections of the oxidant. And so you see that we were able to put them in contact. And even though injections are here and here, this is not sequential, one after the other. Some are contacting before than others. So that's why we need this close-up follow-up in order to know what's really happening. Then we reach the situation when we are able to inject enough mass to destroy COX in this assay or test cell. And here you can see how we can recover that. And the same contaminant load goes back to the early levels, because this was just a test. Now, results at the end of this dosage were this for benzene. This is the baseline, and these were the reached amounts at the end of the dosage injection of the oxidant mass, with reductions in each of the monitoring points for chlorine benzene and for HCH. Here you see the results, how the concentration yields, reductions of 99% for HCH, 80% for MCB, and 95% for BC. We removed a mass of COCs of 5 to 6 kilos. This first assay was useful in order to learn a lot in order to then apply it big scale, both from the logistic point of view and the design of the equipment. In 2019, we were working on all this area here, 700 meters. In this, the strategy was different in this case. In 2016, we only injected in these points here. And these other ones, A, B, C, D, E, are different injection zones, because when we inject, we push the fractures, and we didn't want to drag or minimize the dragging of the contaminant pollutant mass near the injection points. This was the ISCO in 2016 as compared to 2019. So for that, in 2019, we developed an injection equipment which was more agile and portable to move around the site, because we realized that the previous equipment was too cumbersome. It was oversized, overdimensioned. It was hard to manipulate and to control. So we decided to design a more versatile equipment that made life easier. Also monitoring, instead of being having a team of 7 people going up and down, we installed some of the piezometers with real-time monitoring of data that allowed us to manage change and modifications in real time. So we were able to monitorize groundwater levels, conductivity, redox, etc. And also monitoring the persulfate consumption of concentration, the pH control, and also for stabilization and cutoff reaction in sampling before reaching the laboratory, because samples, when you take a sample, there's still persulfate in the jar. So when you take this to the lab, the measurement might be different from the moment when you take the sample. So we need to cut off reactions. And as for real-time sensors, well, you will see it. But when we carried out the analysis, the conclusions were rather significant, and that allowed us to improve the conceptual model. In this chart here, each of these bars are the injection events in each of the areas that are illustrated here in the profile. You can see how in 142 and 142 is monitoring deep fractures. Almost from the beginning, it's starting to monitor that persulfate, injected persulfate is reaching, whereas in borehole 140, it doesn't really get any information up until the last moment, and only because there was a reinforcement in injection in the closest or nearest point. Here again are boreholes in the C zone, etc. So there is a lot of information about arrival times, also dosages. And another interesting thing is that these boreholes that were more that were deeper, here you can see the level of the deep piece meter, and when the injection starts, there are vertical fluxes of the fractures upwards, but then persulfate does not reach until some time later. And in borehole 140 is getting up, and it reaches it later on, rather later on. So at the end, in order to see the direction of the injected mass, it would follow the fastest pathway, reaching 142, and only when injections are done in these closest points, because there are no more piezometers, then it reaches the more superficial fractures of the aquifer. The results of this study allowed us to find concentration yield reductions of between 60 to 80% for HCH, depending on the piece meters, 93% of MCB, and 94% for benzene. It's less than in HCH is less as compared to 2016 because it's per sulfate, because HCH basically is reduced by the application of soda. Soda really transforms it really quickly. But in this case, pH is increased, but not as long, not in that long run. Mass removed was between 36 and 52 kilos, and full-scale test improved the conceptual site model for future injection works. And we also identified the need to drill new boreholes closer to the river in order to distribute better and to attack, so to say, those first meters of the saturated zone, which is eventually would have more contact or more likelihood of discharge into the river. I think I was in time. I was on time. Good afternoon. My name is Alicia Checa. I am studying a PhD student. I am a part of the team of climate, microclimate of the university. I am going to show you the results on our study on the remediation of HCH polluted soils by surfactant, enhanced washing, and activated persulfate oxidation. I divided my presentation in 4 sections. First of all, I'll introduce the issue. Then I will show you or share with you the experimental activities, the results, and I will summarize the conclusions. As you know, contamination of the soil is due to pesticides, and it's a big important problem.
Such as the case in Lindane. As we mentioned in many other presentations, the manufacturing of this type of pesticide generated 2 types of residues, liquid and a solid waste that includes a mixture of different HCH isomers. This solid waste generates the contamination of surface soils, and this is the goal of this work. The soil is contaminated by alpha, beta, and gamma isomers. As we know, they present a high persistence both in soils and in aqueous environments or medium, and we need to develop effective remedy solutions, for example, by chemical oxidation treatments. However, this is limited by the low solubility of the HCH. To solve this problem, an option is the application of surfactant, which increase considerably the solubility of these contaminants, and therefore will propose the on-site treatment of soils contaminated with HCH through the application of surfactant. However, you need to remember that the washing of these soils does not remove the contamination, and we need to treat the emulsions, contaminated emulsions, and therefore we propose persulfate as an oxidant that can be applied with the addition of alkali or at certain temperature conditions. We form different types of radicals that are able to oxidize the contaminant. And therefore, on a first step, we study the soil washing with HCH soils and studying the contaminants that are existing in the soil. On a second stage, we evaluated the oxidation of polluted emulsion, studying the maximum degradation of contaminants to a moderate consumption of oxidant consumption. To carry out this study, we use surface soil of the Bailin landfill, homogenized filtered or sieved, and we characterize this soil. It has a high concentration of contaminants. We see that it has some 300 ppm of the alpha isomer and 350 of the beta isomer. The concentration is in particulates, and to carry out the washing tests, we wanted to use surfactants, one anionic surfactant, sodium dodecyl sulfate, and non-ionic, or two non-ionic surfactants, Twin 80 and Emuls 3. We used it activated by alkali and at high temperature in the experiments. We studied different conditions, pH conditions, neutral and alkaline, and we studied the effect of alkali concentration and surfactant concentration and the application of successive solubilization cycles. For this purpose, the tests have been carried out in discontinuous reactors and with 30 milliliters of aqueous phase, where we have included a reagent concentration and 15 grams of polluted soil. For 24 hours, which is when we think that it has reached some balance, some equilibrium, and with centrifuge. We analyze the concentration of contaminants through gas chromatography, and we analyze the surfactant concentration through the analysis of the total active carbon concentration. And we introduced 10 milliliters of the contaminant emulsion in vials to avoid volatilization of the contaminants. And you can see we used emulse, and after the application of 1 wash and 3 cycles, we got a concentration of 40 grams per liter, and we used temperature of 40 degrees, and we introduced some stirring up. We saw the concentration through spectrophotometry and the concentration of POPs. We evaluated the application of surfactant and the pH conditions. For this purpose, we determined the relationship between the partition coefficient between the contaminant phase and the aqueous phase. This value indicates more solubilization of contaminant. In this figure, you can see the results without addition of surfactant in neutral conditions. As you can see, the solubilization of HCH in the soil is very low. To apply alkaline conditions, the solubilization of contaminants increases significantly. This is due to the HCH being hydrolyzed with trichlorobenzene at a higher solubility. We studied the application of the 3 surfactants in neutral conditions, increasing the solubilization of contaminants. In alkaline conditions, for SDC and emulse, we see a significant increase in the solubilization, but the other surfactant does not reach better solubilization because of the low alkaline nature of this surfactant. And therefore, we wanted to work with a pH of 12 or more, as we see the when we use a twin, we see solubilization that is always less than the ones we obtain using other surfactants, and that's why we rejected it. In the case of emulse, we obtain more contaminant solubilization when using a concentration of 4 grams per liter, and therefore we choose this for the rest of experiments. We assess the effect of the surfactant concentration, and we see that when we increase its concentration, the contaminant solubilization to the aqueous phase increases. However, we need to remember that excessive concentration of surfactant can provoke a reduction of the availability of these contaminants for the reduction, and the surfactant can compete with the contaminant due to the radicals generated in the process. We consider that there is an increase in the solubilization of contaminants when moving from 2 to 5 grams per liter, and therefore we favor intermediate conditions. We lastly assess the application of different washing cycles. As you can see, for both surfactants, we solubilize more than 80% of the contaminants in the soil. We selected the emulsions coming from these wash-ups or washings, and to study the oxidation of these contaminants in the subsequent treatment. In this graph, we can see the oxidant evolution over time. We see higher oxidant consumption in the presence of emulse, and we know that this oxidant is more consumed when we increase the concentration of surfactant in the emulsions that have been treated. Then we studied the conversion of contaminants. We can see a higher conversion when using emulsions in the presence of SDS, regardless of the concentration of surfactant applied. However, in the presence of emulse, the conversions were lesser or lower due to the higher concentration of the surfactant. And therefore, we selected this system, and therefore we eliminated 96% of the contaminants in the soil after 72 hours of treatment. And therefore, the main conclusions in this work are that at neutral pH conditions, the surfactant increases the HCA solubility. In alkaline conditions, it increases their solubility due to their hydrolysis. The TWIM surfactant presents low stability at these pH conditions, and at optimum washing conditions, we solubilize more than 85% of the contaminants in the soil. More consumption of persulfate is obtained when we increase the concentration of surfactant in the presence of emulse, and we obtain higher contaminant conversion rates when we treat emulsions in the presence of SDS, obtaining more than 96% of contaminant removal. Thank you very much for your attention. Sorry that my nose is bleeding. Let's see if I am quick enough. We're going to speak about another technique that we tested in baleen for the plume in the M layer. Well, I think you know what is sparging, so I'm not going to explain it. We're going to focus on the particular application in baleen, the techniques that we've been using, and the results and conclusions. As for the air sparging techniques, well, it is a remediation technique used for the treatment of volatile and non-volatile compounds. The injection in water volatilizes the compounds that have these volatilization compounds, such as in the case of baleen, benzene and chlorobenzene. And the vapors phase is the recovery of the vapors generated by this reaction since its application. In the fractured environment of baleen, we had to adapt this technique to the fractured medium or environment, because taking advantage of the aquifer characteristics, we saw the channeling of the plume in the dissolved phase through the M layer, which is the funnel and gate to channel, kind of funnel and gate, I mean. So those piezometers that are in the site, we took advantage of the fractures and the cracks where the sandstones are presented, because the siltstones do not practically present any fractures, but the sandstones do. And therefore, we injected all the air. If you inject the 3 cubic meters of air, they come out in the same probe. In a normal probe, normally this would not happen. And therefore, this was good for us. So we wanted to take advantage of the fact that the water that is coming into the borehole or into the probing we can recover it and see if we can reduce the concentration downstream. We conducted 3 tests, one in the barrier area, another in the intermediate area of the plume, and the last one in the landfill itself. The main goal in all cases was to assess the total mass removal rate and the total recovery rate of volatile compounds in grams per day. In 2018, we tested and adapted different configurations based on the sparging and vapor station technique using a piezometer, and we used the classic SVE technique. EWAS means E-well stripping, which is a kind of stripping within the probing, taking advantage of the water level being at 25 meters depth. And therefore we create a column for this stripping, which facilitates additional volatility. And we conducted another test with an increase of the water temperature in the aquifer, which gives more volatility compound capacity. In 2019, in the same area as in 2018, we conducted 4 probes, or carried out 4 probes, and we tested the more convenient configuration in these 4 monitoring wells. We tried to couple the vapor extraction and ISCO. You know what ISCO is. Lindane is volatile, don't forget this. And then we wanted to test this combination, seeing if we could reduce the concentrations in the whole range of contaminants. And the goal was to have some control barrier and test more convenient configurations regarding the before we also in the control barrier, we wanted to design a potential plant using ASSVE, so the vapor technique. And in 2021, we wanted to see whether testing would be in a more convenient configuration as compared in 2018, and we conducted 3 monitoring wells in mudstones. As for vapor extraction, we inject air. Air goes through a ceramic diffuser, which generates very little bubbles to increase the contact surface. The gas generated is going to come out through the same piezometer container, which is going to be recovered through a blower, and is going to be treated with active carbon before being released into the atmosphere. Then the second case, the B case, is the biosparging, but using water as a shower. And with these little bubbles, we combine the effect of sparging plus stripping. And the C1, the third combination, is sparging, vapor extraction, and heating of groundwater up to 33 degrees in the test. As it happens in Bailín, the normal remediation equipments tend to be the ones that are supplied by the suppliers, and they are designed for dendritic porous medium, not for fractured medium, and therefore we had to conduct some adaptations. As we know, the quick response of the Bailín aquifer forces us to make a visualization on real time and interpretation later. And this equipment that we designed ad hoc includes POP compounds and it's continuously working, CO2, and the other operational parameters, air injection, total extraction flow, etc., that we can see on the field or here through the mobile phones even that are connected to this. Within the operation piezometer, we have the pump for the IWAS, the ceramic diffuser to create those bubbles in the sparging, and the resistance in order to heat the water. The monitoring was based on 2 large blocks, monitoring within the test point where we recover the air and the gas generated, and 2 observation points, one upstream, one downstream, where we observe water concentrations, the different elements. And so we had active carbon also, and we adjusted the injection rates as necessary. These are the results of the COPs in ppm, the concentrations. We start the system, we start the sparging, the vapor extraction. There is a peak with highest concentrations, and then they decrease and it stabilizes. Every red point is sample taking of active carbon so that we can know whether the rates are the same all throughout the test period. And here, for example, the sparging is switched off, and we only have the vapor extraction, etc., CO2, O2, etc. As we were seeing this on the field on real time, we can know, or we could know when was the ideal moment to take samples. Here we can see more examples, and these are the 3 continuous tests. The first one with the sparging only, the results of the IWAS, and the results of sparging plus temperature. And you can see the down gradient as well. You can see the red line, the chlorobenzene. The initial concentrations were around 25 micrograms per liter. When we conduct the sparging, we see a reduction of concentrations, and therefore that means that sparging is really being successful. But they are never zero, because there is still flow of water with contaminant dissolved coming in. Downstream, the same happens. When we finish the test, the concentrations are reduced. And this allows us to identify the fact that we are able to reduce concentrations in the aquifer. These tests took between 24 and 48 hours, meaning that if we are ongoing surveying this or monitoring, this is a monitoring possibility that is rather affordable and simple to observe how the plume is behaving. The obtained results with the different tests in 2018, you can see the simplest configuration. The total rate in grams per day would be the addition of chlorobenzenes, trichlorobenzenes, etc. 138 grams per day. With the IWAS configuration, 186, and with the temperature plus sparging, 297. In 2019, we selected as the configuration of these rates the highest one. All of them require more operational complexity when it comes to using them daily. The rates seemed so different that with the if compared with the simplest configuration, that using the right piezometer can help us to have the right performances. So we were conducting 4 probings, and we obtain rather high values. These concentrations depend on the load that is dissolved in the piezometer. So more change, more volatilization. As for the vapor extraction, well, this is when we use ISCO. What was a big disadvantage is that we generate big foams with the bubbling, and they even went out of the piezometer, went out of the piezometer, and this was a bad combination to conduct this. In 2021, the one being carried out in the former HCH landfill, the Bailin landfill, you see that the concentrations in the last column are rather lower, which means that the concentrations are lower and there is no water, no underground water renewal, and therefore the performances are less, but it could be taking advantage of the piezometers that are already installed, this would be a way to withdraw more contaminant mass in dissolved phase. By conclusion, I would like to say, or by way of conclusion, I would like to say that in the barrier zone, we built a little house, a little shack to operate and control the plume better. As part of these tests that were going to be done upstream, and so as to have a control barrier, including these actions that have been generated. Out of the little chariot that you saw with the wood, etc., to conduct the tests, this was turned into a more industrial thing where we could monitor and program everything that we needed. So the results and conclusions are going to be given here now.
So as for the results and conclusions, vapor mass removal rates are higher enough to use these techniques. All tests showed that once the aeration began, the concentrations of COX in the groundwater decreased significantly. That means that the contaminant load from the source keeps contaminating the fill of the piezometer. And once the tests were finished, baseline concentrations were recovered rapidly, and higher rates were obtained with the more complex configurations. But in the end, the simplest configuration is recommended from the point of view of the operation in a place, in a site like Bailing. The more complex, the more harder it would be to operate there. And that's all. Thank you. Good afternoon. Thank you for attending my presentation. As Jesus said, my name is David Lorenzo, and I will be talking about the more important outcomes in the pilot test in the Stardust field with enhanced surfactants, enhanced aquifer remediation, which is a project between MGRISA and the Complutense University. This presentation will be structured same way as we have seen so far, with 4 main points. And will be very brief because you already know by heart all the concepts, thanks to the clarity of my previous colleagues. After what we have heard yesterday and today in the morning, in the afternoon, we all know what the problem was, how the Inequinosa factory produced lindane and their corresponding waste, which were dumped without control in Bailing and also in Sardas. Because they are a DNAPL, this DNAPL has migrated and is retained in the interface of the marls, of the fractured marls. As compared to the Bailing landfill, the Sardas landfill has a stratigraphy that's a bit more friendly because it's not that fractured. But the main disadvantage is the landfill is at only 300 meters. Sorry, not the landfill. The Savignanigo reservoir is only 300 meters from the affected areas. The cell of this pilot test is 81 square meter cell, known as number 14. And this is the conceptual model with a fill, an antrophic fill, then silts, and at 15 meters, the alluvial. The alluvial is 3 meters wide, and in this interface between the alluvial and the fractured marl is where the retained contamination is. Groundwater goes through this alluvial, getting this pollution through the contact with this DINAPOL phase, and it has porosity of 30 cubic meters. The enhanced surfactant enhanced aquifer remediation, CR, consists of the injection of surfactant, in this case emulsify, with the goal to solubilize and mobilize DINAPOL for an eventual extraction of both the DINAPOL and the polluted emulsion. On this cell, 3 actions were carried out. First, in July 2018, we injected emulser with a conservative tracer, sodic bromide, and we got the convective adventive model of the Sardas land alluvial. In the second action, emulsitress was also injected, and it was extracted after 48 hours. In both, we monitorized surfactant and COX dissolved in groundwater, etc. But in this presentation, we will be focusing on action number 3, or third action, between April and October 2021, where we tried new injection strategies, and the goal was to recover as much DINAPOL as possible. As I said before, the CR process consists of the injection of surfactant with pumps, with electrical pumps, in different points of the alluvial, whether it was 0.5 meters above the contact with marls or in the alluvial marls contact. 7 events were carried out. In the first, injection was done in 3 wells, in 3 piezometers at the same time. In events B, C, D, E, and G, injection was done in each of these piezometers that you can see here. And in the last one, event F, injection was simultaneously in 3 piezometers in a triangular disposition with a simultaneous extraction in well PS14I. The variables that were modified and analyzed in these events were the concentration of surfactant between 5.4 and 53 grams per liter with different dissolution volumes and different flows between 0.08 and 0.85 cubic meters per hour. Also, we need to leave a rest time, elapse between injection and extraction. That was between 18 and 30 and 391 hours. During the monitoring, the conductivity profile with the alluvial height was determined during the injection event F and the COC analysis in groundwater, and also the concentration of surfactant. Right now, I would like to highlight that event A and F had also a conservative tracer, the same as with the same event in July 2018. The strategy of extraction, once we waited until the elapsed time after injection, we did it with the same electrical pumps, always at a depth of 0.5 meters above the contact with marls or in the bottom of the piezometers. These strategies consisted of, first of all, fluids extracted were sent to sedimentation tanks of 2 cubic meters, and after 72 hours, which enabled to separate the mobilized and the solubilized DINAPOL, which is not very clearly seen here. Sorry, it is a plastic recipient. I don't know if you can see the drops in the bottom. After 72 hours in the extraction tanks, we wanted to separate this DNAPL extracted in a mobilized way. Depending on the concentration, if concentration of COCs was below 200 milligrams per liter, the water was sent, or the substance was sent to the treatment plant. But when concentrations were higher to 200 milligrams per liter, it required the addition of alkali, of sodic hydroxide in order to reach a concentration in the aqueous phase to have trichlorobenzenes. During extraction, we also analyze the concentration of COX, of surfactant, and also the amount of recovered DNAPL. Here you can see a list of the different analytical methods to monitorize groundwater and the extractions, the chlorine compounds, and the surfactants using FID, and also conductometry and ionic chromatography for the other sections. First of all, let's see the results of the characterization of a dense phase of the DNAPL from PS14D in September 2021. In this graph, we can see how composition, the basic composition of this DNAPL, as you can see here, more than 50% is made of these compounds grouped as non-aromatic compounds, non-aromatic chloride compounds, pentachlorocycloxane up to hepta. In this lumping of complex, we include HCH. In addition, chloride compounds and the isomers are linked in CB, DCB, TCB, and TCB. Of event F, the one where we introduced a conservative tracer, we measured conductivity profiles with height in different piezometers. Here in the graph on your left, you can see the dimensional profile of conductivity, where we can determine the dispersion of fluids or injected fluids in the monitoring and injection piezometers. With this, we know where groundwater is flowing in the different piezometers. In addition, by monitoring the flow both of bromide, that's the conservative tracer, both that and the surfactant, we can determine the residence times and the amounts recovered of both of them. Total amount of conservative tracer and surfactant recovered, that's the area below the curve. And we also quantify that of this conservative tracer, we recovered almost 95% of the injected amount. However, for the surfactant, the recovery was only 12%. With this, we can say that what part of the surfactant was absorbed on site, absorbed by the free part in the alluvial. This data is also supported by the results of this study over time, and we see that invariably the surfactant part is inferior than the one of the bromide. As for total mass of DNAPL recovered in over the different events, event A to up until Event D is shown here in this graph, where you can see that the highest amount of recovered DNAPL was as organic phase, as mobilized phase. Maybe you cannot see here, but there is a small red line representing the amount of COCs that are solubilized in the extracted fluids. Maybe you can see it here. This allows us to say that over 50%, 450 grams were recovered. Sorry for the figure, was not clear enough. The amount of surfactant obtained in extractions was also studied. As you can see here, we compare the amount of injected surfactant with the amount of extracted surfactant in red. Again, we confirm that we already knew that surfactant can or is absorbed in the soil or absorbed with B by the DNAPL. When we compare events, we see that event F was the more productive one, the most productive one, and we can determine that time between injection and extraction is an important parameter with a big impact on the amount of DNAPL recovered and is improved with small injection fluxes and extractions that are more energetic. When we compare groundwater from or along these events as compared to the previous years in 2018 and 2020, we see a clear reduction of concentration of COX, so that we can say that we are in the right path. Likewise, if we compare the amount of DNAPL that is accumulated in the piezometers, we see that thanks to the actions or the pilot tests of CR, the amount of DNAPL accumulated in the piezometers is reduced over time. I think the conclusions were already mentioned. I tried to summarize them so that you can see, but I think I am overdue. If you have any questions, we can talk about that later on in the time of questions and answers. Thank you. Thank you, Jesus, for your introduction. My name is Raúl García Cervilla. I will be sharing with you a brief assessment of the application of ISCO and SISCO application in the remediation of the Sardas soil. These soils are contaminated with waste coming from LINDANE production, an obsolete pesticide that was banned by the Stockholm Convention. And the waste from this production of LINDANE caused sources of contamination, of very hazardous contamination for human health and environment. This is also an environmental challenge. Most of this waste is concentrated in Europe, affecting a big number of countries and areas, like the case of the Sardas and Bailén landfills in the north of Spain, in Sabiñánigo. In these landfills, the factory in Quinosa dumped over 150,000 tons of waste, both liquid and solid. This liquid waste transformed into DNAPL with up to 28 different compounds, including several isomers of HCH and different chlorine benzenes. These free phases are accountable for the contamination of the ground, the soil, and groundwater, with a big risk to populations and the Gallego River and the reservoir. As a treatment train, the suggestion, the proposal is the installation of a pumping system for DNAPL that is easier to remove. And after this method is less and less efficient, then we would apply a surfactant injection, allowing for the stabilization and mobilization of the DNAPL in order to keep on extracting it. This must be treated on site. Once the residual DNAPL trapped in the porosity and in the fractures, we need to treat it in situ, for instance, during an ISCO treatment consisting of an injection of a surfactant in the soil and an oxidant. And then the contamination plume should be removed using an oxidant. In this trial, acute toxicity was studied in soils with ISCO and ISCO treatments. These soils were obtained from the Sardas landfill and have been dried and environment at ambient temperature and reduced. We used 2 samples, one of it practically non-contaminated with very small amounts of COCs, and another one with much more contaminated presence of COX. As you can see here, these both soils were characterized where we can find high amount of carbonates. And as for pollution, we can see ACH isomers concentrations and heptachlorocyclohexane. We used 6 glass columns with 50 grams of soil in each of them. 4 of them for ISCO and 2 of them with ISCO treatments. We injected a volume of water pore and then an alkaline solution. Then we waited for the reaction during 24 hours and then we repeated injection. This allows us to transform completely all the chlorine compounds so that they are, the number of contaminants in the sample are reduced. After this alkaline treatment, ISCO and ISCO treatments were applied using persulfate activated with alkali, which allows the decomposition of compounds thanks to the OH radicals. The different treatments, as I said, were used in 2 different columns, in one with 4 volumes of pore and in the other 8 volumes of pore. Here you can see the trial conditions, 210 millimolar, both antioxidant and activator, and then surfactant, emulse 3 for the case of ISCO, 5 grams per liter for ISCO, and 10 for the last treatment ISCO. 4 columns with injection of 4 volumes of pore. After the last reaction, we washed with water with an injection of 8 volumes of pore, simulating the volume of groundwater, and then the columns were dismantled and analyzed, both the phase in the solid phase and the aqueous phase. Contamination in these phases was analyzed using gas chromatography with detectors FD and SAD. Once the treatments of oxidation were done, we carried out an analysis of toxicity of soils through microtox analysis. It consists of analyzing the light cast by marine bacteria. I think I wrote the name here. These bacteria, Vibrio fischeri, in the presence of toxic compounds, reduces its capacity of production of light. Thanks to the analysis of these variations, we can analyze concentration, effective concentration in the sample with the capacity to reduce the power to produce light. We use 3 different methods to analyze toxicity. First of all, the soil phase, both before and after oxidation methods using basic soil phase test, which allows us to assess availability of contaminants, because the effect of toxicity, it's only applied to those contaminants that are present, available for the bacteria. Toxicity in the aqueous phase was carried out using the basic test, and then it was completed using an organic extract using methanol as extractant. In order to compare all the results obtained, we use parameters of units of toxicity that enable us to compare the toxic effect with the numeric value of it. In the next images or illustrations, we can see efficiency of ISCO and ISCO treatments with the COX. As you can see, treatments as ISCO are more efficient than ISCO, and it increases with the concentration of added surfactant. This is due to the fact that when we increase this part, the COX can transfer to the aqueous phase, which are then easier to collect. However, the ISCO process also achieves considerable conversion of these compounds because the oxidation also happens in the surface of the solid. As for toxicity evaluation using this method, one phase is considered toxic or relatively toxic when it has a value of EC50 below 10%. Here we can see the basic solid phase test results, where we can see B2 soil, the one with higher concentration of COX has a higher concentration than B1. And also after application of oxidation, in-situ oxidation treatment application, this toxicity is reduced considerably, reaching very similar values to the clean soil, with an intrinsic toxicity regardless of the contaminants. As for tests with organic samples, we see very similar results. However, the difference in values of toxicity between soil B2 and soil B1 are higher due to the low solubility of the chlorine compounds in the samples that, however, are completely extracted in the organic phase. In ISCO and S-ISCO treatments, the values of toxicity, both experimental and estimated from the individual values of F50 of all the compounds, are very similar. This allows us to say that there are no other toxic compounds in the sample, and in the case of S-ISCO treatments, that the addition of emulsion 3 does not generate any contamination, a toxicity, and added toxicity in the samples after treatments. However, in the sample of contaminated soil before the treatment, the oxidation treatment, we saw a big difference between experimental data and estimated data due to the fact that most of the values of FC50 for non-aromatic compounds present in the sample are not known. And finally, the main conclusions are that despite the high toxicity of the contaminated soil, ISCO and S-ISCO treatments allowed to reduce considerably, and that these results can be or are very much related to the reduction of total COX in the sample. In addition, application of emulsion 3 as a surfactant did not show an increase in soil toxicity after the treatments. And we can also say that treatments ISCO and ISCO treatments can be proposed for real application at full scale because they allow to reduce, at least on laboratory conditions, toxicity present in contaminated samples down to values similar to clean soil. Thank you very much to the funding that made this work possible and the collaborator partners. Thank you all for your attention. Thank you, Aurora. Yes, my name is Julia Isidro. I work for the chemical engineering of the University of Castilla-La Mancha. I will be talking about design and validation of electrokinetic techniques for the remediation of the alluvial silt of the Sardas landfill, contaminated with HCH. First of all, I'd like to explain what the electrokinetical technologies are. They consist of the application of an electric field injection directly in the soil. This electric field creates movements in the soil at macroscopic level, microscopic level, like the movement of charged species and due to electrophoresis, and at the molecular level, movement of ions in the soil via electromigration. In addition, the compartments, there is water electrolysis. In the anodic compartments, through the oxidation, we would generate protons, and in the cathodic, we would generate other fronts. We have the acid front and the basic front. We would also get heat up of the soil, making compounds with a higher volatility to be a part of gas phase. In our team, we have been assessing efficiency of the remediation with kinetics for the recovery of pesticides, organochloride pesticides, both in laboratory and in different volumes at the small scale, also pilot project with 32 cubic meters. So we look for remediation techniques of contaminated silts. By MGRIS and the government of Aragon, they wanted to count on us for this, to design and validate electrokinetic techniques for the remediation of the alluvial silt of the Sardas landfill contaminated with HCH. For that, we carried out some tests at 3 different levels. So the first ones are at laboratory level. The main goal was to establish the transfer of contaminants in under controlled conditions towards a gas phase inside the soil and towards the liquid phase. To interpret the experimental results, we used a model based on the equation of a matter balance, and the main adjusted parameters are dragging velocity, diffusion rate, and lambda rate, directly connected to the volatilization velocity of compounds. To evaluate the transfer of contaminants from the contaminated silts towards the gas phase, we carried out these types of trial to introduce lime silt in a tank and inject an airflow. These experiments were operating for 7 days at 25 degrees. The result of the adjustment of the experimental data, we obtained the different results depending on the different compounds classified depending on the name of chloride. As you can see, compounds with less number of chloride show higher rates of volatility, but we also need to keep in mind that lindane and delta HCH have normally high rates, maybe because they are in higher concentration in the silt. Once we know this, we carried out another study to estimate transfer or transport of COCs in the soil. For that, we used this sort of model, and we introduced a portion of contaminated silt inside a clean matrix. We carried out several trials at ambient temperature and 50-degree temperatures to establish the impact of temperature in the transport. Here we see, as an example, for lindane, the distribution of contaminants obtained at the end of the experiment, with a point showing experimental data and lines showing obtained values after the adjustment with the model. Thus, we were able to estimate dragging velocities and other parameters, and in all the cases we have correlation rate higher than 0.9, which is rather positive when we are working with experimental data. We also show concentrations of this compound not reaching anodic and cathodic wells. As you can see, they are pretty low, around 10 minus 5. And this model was applied to the other families, and we can see here the comparisons with the results of the ambient temperature and 50 degrees temperature. As you can see, diffusion rates, there's no clear trend. It's around 0.5 centimeters per day. However, when we estimate dragging velocity, we see that contaminants, when we work on a higher temperature, look as if they move around the area of the cathode, maybe due to the volatilization, because we are working under higher temperature. And in the case of temperatures at ambient temperature, we see that those with compounds with higher number of chlorides, they move towards the anodic area. We can conclude that there is a volatilization of contaminants at 20 degrees, and this is affected or impacted by the temperature. Once we know how contaminants were transported under controlled conditions, we wanted to take a step forward and see how transport is affected by conditions in real life. For that, we took 10 unaltered samples from 5 boreholes in 9.5 meters deep and 12 meters deep in the region where the silts are. We took an electrode as reference, as a baseline, in order to establish the initial concentration levels related to depth. These are the results. For that, we see the central pole sectioned in 5 sections, showing the total concentrations of millimole per milligram of dry soil. There is a big dispersion of data, even though it looks as if concentrations higher as we go down and down. We also took samples of the extremes of unaltered samples, and were presented according to their depth. Here we can see how there's a big dispersion, so that we can conclude that this dispersion is not just in the vertical axis, but also in the horizontal axis. If we estimate for the same samples the number of molecules, it's always around 5, which can make us conclude that silt has the same rate of aging. This will make the comparison difficult, the comparison of trials. That's why we would take the central pole as the reference. In order to carry out the experiments avoiding or without breaking the structure of the soil, we use this sort of system with PVC materials and the anode and cathode connected to reservoir tanks, and we were taking daily samples. We did 10 tests to study different role of different parameters, such as the introduction of the electric field, both vertical and horizontal, the treatment time, addition of washing fluid, a reversal electric field introduction, and introduction and a higher number of volts per centimeter. When we apply electrokinetic techniques to soils, we normally use constant potency. So we monitorize intensity and time. For the case carried out in vertical and horizontal, we see how intensity increases and then it decreases and then it keeps stable. Intensity gives us information about velocity of processes, of electrokinetic processes, and is directly related to the content of water in the sound and its ions. Here we can see measured volumes in anodic well and in the cathodic pole well, and because we saw the directions, we saw how the volume was disappearing in the cathodic well. Thanks to this, we can see the electrosmotic flux around 0.8, 0.7 centimeters per day. As for mobility of ions, we also monitorized it in the anodic and cathodic wells, conductivity, and concentrations of some of the ions, the type. These were reduced and then they kept stable. Same with chloride ion is accumulated in the anode due to its charge, and respect to pH, the values are pretty acid in anode and basic in the cathode at the beginning of the experiment due to the production of protons and due to the oxidation and reduction of water that would travel through water. We also analyzed HCH compounds reaching anodic and cathodic wells, and we could see in terms of millimole as compared to initial millimole, and we can see how in all the cases it was below 1%, so this concentration is pretty low. Once we finished the trials, we carried out the post-mortem analysis, so fractioning the poles in portions of 5 centimeters and analyze the organic content. Here you can see in terms of total concentrations per kilogram of a dried soil, the black lines are initial concentrations as measured in the central tube, and then in the different moments, and green dots are the final results in the post-mortem analysis with a big dispersion of data that doesn't allow us for any conclusions. If we analyze the number of moles per molecule, we see a reduction of these parameters around the cathode, maybe due to the alkaline movement. If we compare the role of different strategies of applicability of this treatment, the effect of gravity, we saw there are no differences between working in horizontal or vertical modes. On the opposite, if we add a washing fluid, this does not seem to have any effect. When we add the value of the electric field, it is clear that the advances of the basic front are higher, and the higher electric fields applied. In the end, we have along the pole or the tube molecules with average chloride below 4. With the case of applying a reversal field, it's not just reduced on one end, because the electrodes are moving both directions, they are being eliminated both sides. And when using shorter cycles, they seem to have better results. Here we can see concentrations in terms of percentage for one of the tubes. At the beginning, in blue, and in red at the end. At the beginning, most of molecules are ACH, and at the end of the experiment, these have dropped, and we have less chloride molecule compounds. So we can assert there is a low mobility of contaminants but high dehalogenation. And finally, thanks to the learnings during the experiments and taking advantage of the boreholes, we set up a pilot test in Sardas with a central anode, 3 cathodes to favor dehalonization. And because we think temperature will raise, we have installed these carbon filters to catch the contaminants that can be volatilized. I just would like to say thank you to EMGRISA and the government of Aragon for funding and supporting these projects and the organizers of the forum. Thank you for your attention. This is the last presentation. We are pretty tired. This is sort of repetition as what Julia just said. I will try to be brief, only insisting on the ideas that I like for all of us to be clear on. We carried out this study within a bigger project funded by the research agency. We have been honored to be able to collaborate with the government of Aragon and EMGRISA to apply our strategies to one of the leachate ponds in the Sardas landfill. Okay, I will just introduce very briefly. You all know how to localize to where this picture is. We are focusing on the lower part with the leachate pond. This old leachate pond. If we have a look, the pointer is also exhausted, I'd say. If we see it from the sky, we have 2 leachate ponds. We have 2. You see the old one and the new one. From the point of view of a dismantling, a safe dismantling of the pond, localization is not particularly good because here we have the reservoir. So any issue that might come our way could have really serious consequences. We hope not. In the lower part there, it's just 1 meter from the alluvial. That means dismantling must be very, very careful. Other additional characteristics. Here you can see the conditions of it in certain times of the year. Inside this pond, we have around 1 meter of sludge that is rather heterogeneous. As for concentration, some milligrams per kilo, milligrams of COX per kilo of sludge, or even several tenths of kilos. It was also sent to the dense phase, and this is also like, so to say, a long mechanism. I was saying, and due to the localization and characteristics, dismantling must be very careful because it could affect groundwater and the Savignanigo reservoir. So we should try to avoid to damage the layer, the protection layer, avoid filtration or leakage of leachate, or affecting surface water, and everything from the point of view of safety, of health of workers, etc., and health of the population around it. Now let's have a look at the sludge. The sludge for us is a matrix of solid that can behave almost like a soil. Visually, is quite dark. And on the surface, the color is a bit lighter due to oxidation, but from the point of view of the treatment, electrokinetic treatment that could work here, it has very plastic features, it adherent, it's difficult to handle. It is a sludge that is rather compacted and saturated in water. So it's not a lime, but we thought it could have positive features in order to apply electrochemical strategies so that we could get safer sludge to be extracted. We already saw this. We're going to insert electrodes and apply an electric field and try to apply some of the processes that can happen in the soil. Many processes. We can have electrokinetic processes themselves of mobility. We can move water, we can move ions, but we could also be interested in other parallel processes and try to develop them also. We saw how electrolysis can happen, oxidation and reduction of water. We can create protons and ions of hydroxyl in the cathode that can favor the halogenation of the components of the COCs in the sludge. These are ions, so they would be moving thanks to the electric field. And on the other hand, heating soil, the basis of this sludge can generate heating of the bed, so that everything that can go into gas phase like water and everything that can be volatilized would transfer. This is our objective, to dismantle this highly HCH polluted landfill leachate pond. Being optimistic, we thought that we could reach a level of dryness appropriate for the sludge to be handled mechanically, which is the easiest way, and try to minimize the atmospheric emissions, uncontrolled emissions. We don't want it to get to the air, and minimize the needed infrastructure and equipment. And this general objective, we translated into partial technical objectives. You all know that without any prior tests, we cannot really know how to move around. So you see here our partial objectives. First of all, how our pollutants move, see how we can dry them, the watering using the electric field. If we move water, let's see how the water is, how can it be treated using electrochemical technologies. See if we volatilize, we have to see what we do with those pollutants and then implement the technique. After this, we structured results. Let's move forward. Just let me know if I reach my time. I would just go over this. First of all, we need to analyze mobility under very controlled conditions, because otherwise there would be parameters that would not be controlled. So we carried out laboratory scale trials. We inserted the poles, the electrodes. Julia talked about this. Poles can be inserted directly in the soil or in electrolyte wells. We would use the first option. we're going to insert these electrodes directly in the soil. This will be connected to our power supply or power source. So we carried out different tests with different cell potentials, and we analyzed the parameters shown by Julia before about the behavior. We have here 4 HCH isomers, and seeing the dragging velocities clearly increased when the electric field was applied. We also analyzed how these COCs were volatilized. The results are very similar to what you already know. Then you are optimistic and you forgot about controlled conditions, and you think you're going to get the same things, the same results in the real place. So we prepared these trials. We carried out these samples, which were practically plastic containers of around 50 grams, and we analyzed different, 50 kilos. In the kinetic samples, we also thought about additional SPS in order to see if mobility was enhanced. And we tried to see what happened to the electrodes of iron. In this case, the installation was pretty easy. We used shallowed holes so that fluids could be pumped easily. Now the system was covered, and we induced an air current for those compounds that could be volatilized and be trapped in an active carbonated column. So we registered intensity, which was going to give us the velocity of the process. The higher potential, the bigger the velocity. We saw how clearly intensity increased during the first days, but then it dropped after 10, 12 days. I will show you a logarithmic graph so that you can see it in a in an easier way. This is important because this is the main operational parameter. Ideally, if I inject high power, velocity should be higher, but we saw that the trial intensity dropped to minimum values, then there is no mobilization, and it looks as if it worked better in the trial with softer conditions, because we were able to keep a velocity at not high levels, but at least enough for mobility of water. And then we saw that using iron electrodes, iron really helped to keep those levels of intensity, of conductivity in the system.
Why did that happen? In this photograph, you
can see here the hollow
just
holes, and we see how
for the electrical
sludge
contact
starts cracking
the screws,
significantly, so there is no continuity. If there is no continuity, the ionic circuit is not closed, so that's why intensity was dropping.
Close, and this is why it was unsuccessful.
So we move some of the water. It goes from anode to cathode.
Goes from anode to cathode. Here, only in the anode it was recorded because in the first days the water was coming out here, but not due to moving it cinetically. The intensity is similar to the one we saw, and the important thing is that what we saw in the case of intensity, we were able to withdraw more water, and we wanted to dry the floor so as to facilitate the better handling. If we analyze the final values, the amount of water mobilized decreases with the electrical field because of this cutting intensity. But you see how the amount of water evaporated increases with the electrical field due to the heating of the soil. And you can see it very clearly how the droplets were condensing on the cap. And well, you see how it's going to acid, it's going to basic. We measure conductivity. We measured also the organics mobilized with water, which was very, very low. And the contaminants are so strongly adhered to the matrix that it was very difficult to mobilize them. And with water, it is impossible. And in the post-mortem analysis, similar to what Julia was saying, the good thing is to see the concentration profile. We have a lower concentration than in deeper levels. And obviously what is more exposed is what is being more withdrawn. And we had the H2, the hydrogens in the cathode area. This is the anode, this is the cathode. And you see that the number of chlorines per molecule, they drop. And this is the halogenation. And everything is more volatile and everything is in syntony. As for the other parameters, I'm going to skip this. This is the contaminant distribution here. This is the initial distribution. And we have here the family of HCHs. You see how extreme conditions, its relative proportion has decreased in the case of HCH and trichlorides and tetras. Our suspicion here is that the organics retained inactivated carbon, the moment they find somewhere to condense, like the droplets on the lid, they condense. And therefore, in the final treatment, we need to put some trap. I'm going to skip the conclusions and I'm going to skip the water treatment part. And I would like you to see how we tend to try to dismantle that or decommission that. We don't want to decommission or dismantle the pond unless we make a test. We need to have access there with our thinking minds, the thinking minds of Embrisa, the government of Aragon and ours. We defined a platform to have access to the whole treatment area. And this is going to be isolated with panels. And this is a floating platform. And we are going to install some panels in order to treat this area. And we are going to locate some electrodes at 1.5 meters. These electrodes have been chosen. The material is iron. They are perforated. They are hollow. And so that when we need to pump any fluid, we can do that. And as we need to volatilize, we need to cover them. And we are going to put polycarbonate on top so that, or a polycarbonate plate to cover that. And in this system, we have the liquids generated on the one hand. On the one side, we are going to take them to treatment. These waters are very lowly loaded. We perform some Fenton treatment. with diamond electrodes, but maybe they are waters that are very lowly loaded, as I said, or with a very low load. And maybe a solution in active carbon would be okay. In the case of air, the cooling tower to remove those droplets is very important, and as well as soda absorbers, so that all the gas that we extract, we can get it. And so the whole system is very well thought about. The equipments are bought, and today this is under construction. If you come on Friday, you will see all the equipment which is available to be implemented. You know that any kind of action needs to be done according to very strict safety levels, and this is what has delayed us a little bit. I would like to thank you for your attention and the confidence, the trust by MGRISA and the government of Aragon in us, on us. Thank you. As you have been very fast, all of you have been very fast. Let's open a discussion, a Q&A and a discussion. This has to do with what we saw yesterday and today. It's not necessarily associated to today's session. So the question is for hydrogeologists in the room that are involved in characterizing aquifers in Sabiñánigo, both from the government of Aragon and also the ones coming from the companies that are monitoring the hydrogeological developments. I wanted to know whether you have characterized the contaminant mass in the low permeability formations, and in particular within the matrix, the rock matrix of those fractured mediums. And this is important because we tend to focus on the contaminant migration through advective mechanisms, which is logic in high permeability mediums such as fractures. And this is important because we need to contain the dissolved phase that can get to the Gallego River. But from the point of view of the DINAPLE, it is very important to take into account as well the molecular diffusion that is taking place, that makes that a lot of mass is accumulated in low permeability formations as well as in the rock matrix. What we saw in many sites in the States and in Canada is that even when you have cleaned the fractures, you still find a lot of contaminant DINAPLE mass within the porous medium of the matrix, and this needs to be characterized through high resolution methods at pore scale. Why is this important? Because in sites that have been releasing contaminants for a very long time, we saw cases where there were no more contaminants in any place except for in the matrix. And due to reverse diffusion, this comes out again very slowly, very gradually, and we take years and years and years in trying to solve those problems. And the other thing which I consider important is to get to know how much mass is in the rock matrix and what is the reverse diffusion rate. Because otherwise, when we apply DINAPLE recovery technologies or remediation systems, be it with surfactants or oxidants or any, or iron, valent iron for the solubilization, mobilization, or destruction of DINAPLE, we need to know what is the reverse solubilization rate so as to know how much agent we need to inject. I'm going to answer. As we have different matrices, we need to differentiate. In the Bailin case, the rock matrix or the rock aquifer, well, there are siltstones and sandstones that are highly cemented with no secondary porosity. And they are fractures associated to fractures. And when we take probe that serves as a reference or a control probe, when we separate ourselves a couple of millimeters, we don't have contaminant. In the baleen case, this in rocks, the contamination hasn't been very large. After 2-3 months, we haven't seen any rebound effect. There was absorption. Obviously, a large part has been recovered, in the decalcification places or processes near the fractures. In the case of sardas, this is different. In the case of silt stones or silts, they are detritic silts with very small clay fraction, and therefore the retention is in the very small in the porous system because of a very low permeability. But there is no retention, that retention that we could see in certain clays, which would be interlaminar retention that would be very slow and very difficult to extract. At the moment, in the treatments in the aquifer, we have been extracting with surfactants, and we will have to make an SISCO campaign to see whether there is some rebound or not. There is obviously a clayish fraction, and this will have an impact on the matrix.
Jesus, maybe you can add also the marls, yeah, the what we call FAD, huh? the rock which is fractured, decompressed, and weather, yeah. That is another story, right? So you want to comment on that?
Yes, one of the sardas problems are the marls, weathered marls, in fact, because we observed that some droplets of DNAPL at 40 meters depth in controls that were not even fractured. They were having like dendritic bands or stripes. And this is where we found those droplets, DNAPL droplets. And this, without using relatively destructive techniques, this is going to be difficult to get rid of those, really. And in the higher part of the marl, where the contact part, we find a similar situation, because even if the marl is weathered, in some occasions, in the end, it is even less porous. I mean, the healthy marl is even less porous because part of the carbonate has disappeared, and therefore there is a material that is rather plastic and very non-porous, practically non-porous. And in these cases, it's very difficult to use any reagent in those materials. In the case of deeper marls, as the circulation regionally is really slow, this is not of no concern to us. We're more worried about the alluvial contact between, the contact between the alluvial part and the marl. And we are working on the solution, but we haven't found any yet. I just wanted to mention that there are techniques, extractive techniques that have been used in other sites, particularly those with DNAPL associated to organochlorinated solvents in boreholes, and they used different tools such as the magnetic resonance or nuclear magnetic resonance techniques, for example, kind of MRIs for granular textures. There are experiences and there's literature describing this. with the borehole profiling in both cases, in, for example, nuclear magnetic resonance and with mathematic modeling, we have determined molecular diffusion rates in the DNAPL. In most of the cases, it is preferable to use reference or, sorry, controls. But if the controls are not representative enough, we can use the borehole geophysical profiling. We can even be more direct, because if you have probing control, you just take your control, you dissolve and you analyze, and we can do that with no sophisticated techniques or anything else. The marl, the weather marl problem in the Sardas case, it's not whether it retains or not DNAPL. It does retain it. The problem is how to extract it. Yes, I don't see the second speaker, the one who mentioned the gels. Yeah, the French speaker, he's seated at the bottom, Antoine Joubert. So the question is very specific. If I inject gel, in this case, in the rocky area, how would how the phreatic would be modified, especially in high waters, because in this double porosity, highly fractured material, how can I monitor that? How can I control? Because, or maybe this is what I want. I want to modify it so that the flow crosses this gel part. Can you explain that?
Thank you for your answer, for your question. I think the gel has some rheophytic properties. So I guess it can propagate in this type of material, this type of fractured material, even if in the thinnest fractures, where maybe we have capillary tension that block DNAPL mobilization. So I'm not sure, but I guess it would be interesting to try in this type of structure, of this type of geology, to inject gel and surfactants to mobilize DNAPL. But I don't know. We need to test it. We've never done yet.
I have another question related to your presentation. First, for all, thank you very much for the presentation. We are very, very interesting. In the case of this polymer, the gel you are using is compatible with oxidants, or could be destroyed if you add an oxidant with the...
Yeah, we already tried to get an oxidant in the gel, but unfortunately there is a bad interaction with polymer and the oxidants, so the oxidant consume part of the polymer. So we are working for another type of gel, which is inorganic one, so we can inject gel, so gets all the great properties of rheophytic gel, but injecting oxidant also. So it's research and development.
Yeah, because the only reagent was the sodium hydroxide. So you need maybe for other application other reagents, not like oxidant, to destroy the pollutant. So yeah, encourage. I hope you find a gel.
I hope too. Yeah.
Yeah, and more questions.
Thank you.
Welcome. For Jeroen, I had Jeroen is there. Yeah. I had a question about the radius of influence, because maybe I understood bad, or I don't know if I understood you inject in a position, but the fluid you are injected is distributed far away. How is the radius of influence of the injection?
Yeah, The radius of, it's a good question. The radius of influence is determined by the volume that you inject. So the larger the volume, the larger the radius of influence. And it's also determined on the soil type. So if you inject in a sandy soil, you inject in the macropores, and the sandy soil is almost 100% macropore. So if you inject 100 liters in a sandy soil, you can reach a radius of influence of maybe 1 meter, half a meter, 1 meter. If you inject the same volume in a clayey soil, where you have only maybe 5% of your porosity that are macropores, you have a radius of influence of 3, 4, 5 meters. So it depends on the volume and on the texture, soil texture.
I understand that this methodology is used to apply reagents that you don't need to recover, so as to apply in situ or on the field. You don't think about recovering these reagents in low permeability mediums, right, Jeroen?
No, so our system is made to inject reagents indeed. And with the system, it's not possible to recover the chemicals, but sometimes we also inject, for instance, surfactants that are recovered in wells on several locations. So there's a grid of wells to recover the product, the reagents, and we inject the reagents in between the wells. But directly with the system, no, we can't recover it, no.
The way you show in the image was an helix. So in clays or sand soils, it is effective and pores are not reduced. But in stone, in rock, do you use another head?
In hard rock, we can't, it's too hard, you can't get in it. But in marl, so we already injected in marl in France, and it depends on the amount of calcium carbonate, and so the hardness and the porosity of your marl. But we also succeeded to inject reagents in the marl, yes.
It is affected the duration of the barrier for the composition of the groundwater. For example, if there are many organic compounds dissolved are competing with the PFOS. So what is the case better to apply this barrier, or what cases are not adequate for these barriers?
Yeah, we need to take into account any compound that can sorb to the activated carbon, which can be other organic contaminants or natural organic matter. This, more than the longevity, affects the design, so the amount of carbon that we need to place into the subsurface. The behavior then would be different because all the other compounds, except the PFAS, would then suffer biodegradation. So an organic matter would sorb to the activated carbon, but then would degrade and would free up additional sorption sites on the activated carbon. So on the longer term, this does not affect. So I wouldn't get saturation breakthrough of a barrier because of organic matter or because of, I don't know, chlorinated solvents, petroleum hydrocarbons, etc. What then on the longer term causes the breakthrough, it's PFAS or non-destructible contaminants, persistent contaminants.
Okay, so for non-biodegradable compounds, it lasts for a long time, no?
Exactly, exactly. But I mean, with PFAS, well, luckily, into most of the plumes, we are talking about nanograms per liter. So the flux mass, usually in terms of how many grams per day are arriving to the barrier, it's very limited. And this is one of the reasons why we can last such longer term. Of course, with pure sorption, you couldn't manage plumes that are at higher concentrations.
Thank you. So yeah, I see everybody is standing up. So thank you very much for the attendance.